Let's today, hello students. We are going to start with today's part. Actually, what we are going to do, our part, I'm going to take the mayor's relation. What is part here? We'll be working with the mayor's relation. Okay, so mayor Mayor's relation related to the specific heat of gas. It's not our mayor, what we have in our cities like that. So we'll be working with that part. That is our mayor's relation. So let's start begin with the original concept here. So we'll start in this one. Now first part, let's go for the basic definition of heat capacity. What is heat capacity? So heat capacity is Q upon delta T. That you are well aware that mass M absorbs heat Q. The temperature rises to delta T, that is the rise in temperature. Remember, this is your rise in temperature. This is a rise in temperature there. Okay, fine. Rise in temperature. What is the temperature? You can say the final T final minus T initial, or you can say T2 minus T1. This will be your rise in temperature. Now, what is C? C heat capacity per unit mass. That is heat capacity per unit mass. So, substituting the values, we'll be getting Q upon delta T. That is already this one multiply M. So, M will be in your denominator. So, we can get Q upon M delta T or theta. I mean, this is also used. Theta is also used for to indicate change in temperature there. So, this is another part. Another way we can represent that method of representing. Anyway, any notation you can use delta T or theta. Now, specific heat. Now, the specific heat of the material is defined as quantity of heat required to rise the temperature of unit mass of material through 1 degree centigrade. So that is in degree cent. CGS will be per degree centigrade and it will be joules per kg per degree centigrade. Here it will be, sorry, it will be per gram per degree centigrade, grams per degree centigrade, joules per degree centigrade. So this is a specific heat of the material now. Okay. So let's begin here further. For example, if you consider specific heat of water, that will be your 1 gram, 1 kilocalories, 1 calories per gram degree centigrade in CGS units here. So converted, if you are converting that into kilocalories, you will be having kilocalories per kg degree centigrade. So to convert that will be, it will the value that is joules specific joules constant will be using 4.18 into 10 to 3 joules per kg degree centigrade. Now, the part is that condition will be gas are compressible and the specific heat of gas may vary from 0 to infinity. This is the ideal condition, infinity. It may, for example, now if gas is compressed, the temperature, now see this diagram, we are compressing this gas here below, according to arrowhead is shown downwards, we are compressing that. Temperature rises without supplying any heat. So at that time, the heat is, no supply of heat is there, so that Q equals 0 and C will be now C will be Q upon M into delta T. So no change in no heat supplied. So numerator is 0 as usual, like mathematics denominator. The total value C becomes 0. Now if it allows to expand freely without rising temperature, if delta T becomes 0, now its denominator is becoming 0 here, then it will go to infinity. This is an ideal situation or undefined. What we got in mathematics, how we say 0 in denominator, it goes to infinity or it becomes undefined. So like that, this CV is going to become infinity in this case now. Now further, we will consider two specific heats, CP at constant pressure, specific heat, CV at constant volume, the specific heat at constant volume. Now what is CP and CV? So what is the definition CP? Amount of heat required to raise the temperature of unit mass to 1 degree centigrade when pressure is kept constant. Pressure kept constant, delta Q upon delta T. Change in 1 degree, increase in rising the temperature. We have to raise the temperature here. And in this case, similarly, CV, what it is, we are going to raise the temperature of unit mass to 1 degree centigrade. Here, volume is kept constant. What we are keeping constant? Volume constant. That will be your CV. So, delta Q upon delta T at constant volume. So these are the two definitions for CP and CV. Now we are applying this CP-CV condition. Now, what is the condition? CP is always greater than CV. Remember, CP is always greater than CV. So heat supply to gas is allowed to expand at constant pressure. Then it rises the temperature of gas. Increase. Now, a temperature increase means what is internal energy is increase. Since you are providing heat energy, heat is nothing but internal energy. Energy. So it does work. Now, in this case, what happens? It does work in expanding the gas against external pressure. So work is done against expanding the gas. So dq is equal to du plus delta w. That is the work done. Work done, I am writing formula P into dV, the pressure into change in volume, that will be our work done. Now see, As gas is heated at constant volume, no work is done. So delta W will be equal to PdV. That is equal to 0. If hence whole of the heat is supplied to you to use the raised temperature. See, whole heat is used. Where it is used? To raise the temperature or raise its temperature. Yeah. Raise the temperature. The more heat is required for increasing the temperature of heat through 1 degree centigrade at constant pressure. What is that? At constant pressure we are going to see that. Then the volume, constant volume, what will be? And Cp will be greater than Cv. Huh? So this is what the concept is applied, or this is what the concept why we say that Cp is greater than Cv. Mhm. Now let's find the relation between Cp and Cv there. So I'll go step by we are working here Cp and Cv. Now first part, consider 1 gram of gas at a pressure P, volume V, heat supplied to gas to raise the temperature through dT. As pressure has to remain a constant, work done will be equal to P into A into X. That will be, now A into X is area into the displacement, so that becomes the volume, that is dV, that is the volume, pressure into volume here, right? Work done will be pressure P into A into dx. So now this where dV is a change in volume, because initial volume in the gas is present and we are changing that volume, so we can't say the total volume of gas, the volume is changed. So we'll call that dV as a change in volume. Now we have equation for this, PV equals RT, origin equation. If you are multiplying with N, it becomes PV equals nRT. Just remember, if N number of moles is there, we are aware of this is common gas equation here. Here we are considering only RT first initially. Now 1 mole of gas. So PV plus VdP is equal to RdP. Now this is what we are doing differentiating. We are taking differentiating means taking the derivative here. We are taking derivative here. So derivative V gets converted to dV here, and plus V into dP. P becomes dP. This is well student, well aware. This is your product rule. Remember, this is your product rule and differentiation. What we are using. That means as you know that x into y becomes as usual x into dy by dx plus y into 1. This is how we solve in mathematics. So this product rule is applied over here. We are applying product rule here. So p dv plus v dp is equal to r dt. Now here part is that p dv differentiation is taken. P into dv is equal to r dt adjusted here, but dp is equal to 0. Now condition is that change in pressure is 0 here. So applying this becomes 0. So as a result, PdV is equal to RdT, substituting the 0 value. So now work done in heat, that will be RdT upon J kilocalories. So we have to convert into kilocalories, the heat unit joules to calories. Joules to calories, so we are dividing with joules constant there. So heat supply dQ will be equal to 1 into Cp into dt here. Now we have formula for that. Now according to molar specific heat, now molar specific heat du is equal to 1 into dV Cv into dt. Remember, this is at constant pressure, this is at constant volume. Now, first law of thermodynamics, we are applying these formulas, whatever we have derived. We are implementing or substituting those formulas in first law of thermodynamics. First law, remember. So, dq is equal to du plus dw. So, dq will be equal to 1 into cp into dt. So, what is du now? 1 into cv into dt here. Plus r into dt by j. So, work done will be r dt of j. So, we will be getting cp equals cv plus r into j there. And finally, once transposing on other side, you will be getting Cp minus Cv is equal to R upon J, where R is called as gas constant for 1 gram of gas. Cp and Cv are specific heats at constant pressure and temperature. And if you are replacing this small r with universal R as a universal gas constant, we'll be getting a relation Cp minus Cv is equal to R upon J. And this is called as Mayer's relation. One of the most important question here. Mayer's relation. That is the final. This says that Cp, the difference in the specific heats at constant pressure and constant volume, is equal to R, that is universal, R upon J. Universal gas constant divided by, when converted to calories, divided by J, we are just converting that into quarters. So this is the part we got the Mayer's relation. Okay, thank you.